So one last problem that I'm going to show you is on page 334, exact same page, problem number 10. So essentially we do the similar things, but this time is the also use the divergent theorem, the Stokes theorem. I think it's still Stokes theorem. Yeah, Stokes theorem, and do the calculation like this. So what you do, you can choose whichever you want, and we do the almost identical things as we did previous problem. And this is the line integral v dr. Now the v itself, if you look at the book, v itself is just this part, so you can see clearly without any problem. So this is the v part. Now what I need is just express them out in the sense they have a vx, vy, vz. This is the dotted product. You see that? So total we have 3 terms there. And if you just reflect back what we learned before, this term essentially p. This term is essentially q. Now if you have third term, this is called r. And so that's the Green theorem. Essentially you have 3-dimensional. Now we do the same thing. We choose a line path. Since we were given an equation, it's a little bit complicated. It's just equals, let me show you here. That's the equation we were given here. So this is the equation. Did you see you have z equals 9 minus x squared minus y squared. So in that case, I also let z equals 0. So then I have very nice ellipse on the xy plane. So again, I choose the surface above xy plane. That was the problem was asked for. So that's what I'm going to do here. So now my line equation looks like this. Same trick, I replace them with the polar coordinates, and I have 3 cosine x along the x direction, y just sine theta. So that's all I need. And then substitute the entire things into the equation, and then do the integral. You see now we do start from theta 0 all the way to 2 pi. And now reason I always start from 0 to 2 pi is because it says in the problem it's above xy plane. I hope you can read this, but it's above the xy plane. If in exam, if I say below the xy plane, then you need to reverse this 2 limits. Instead of from 0 to 2 pi, we come from 2 pi to 0. Essentially, it's a right-hand rule. You first clockwise this or anti-clockwise the other way around. So that's the different directions. So once we understand that, and then we can do the terms by terms. So total we have 3 terms that we're going to do one at a time. First with number 1, and then number 2, number 3. So the first is number 1. We substitute that into it. So you see we get a 0. Second term here is get negative 6 pi. And we do the same thing. There's no other trick. And the last term is because z equals 0, so it's 0. So then we just add them up. Eventually gave me the results is negative 6 pi. So that's it. So I hope you enjoyed the video so far. If you have questions, please let me know. I strongly encourage you to work out some of the other problems, like this one here, which is also pretty good. And this one is also here pretty good. So just to give you a little more exercise. And these are the Stokes theorem is one of the most complicated ones. And let me make a final remark that I probably skipped this a little over here. Now in principle, for the previous problem, number 8, like this, in principle, I could also do the surface integral, but this one's non-trivial. Non-trivial things was the following. Here, did you see here's n? Which direction is n? This n itself is an ellipsoid. So ellipsoid, which means the direction you have to make sure. So in other words, if you really insist to that, you have to change these x here and z there, change to so-called x prime and the z prime, such that make this n along the spherical direction, the r direction, and then the answer should be durable. But when you change that, you have to make sure this k, these vectors keep as they are, but you need to replace these ones. And also the surface portion of this also needed replaced. So in many ways, it's a little bit more complicated, but it's durable. by all means. So that's I just want to make a remark.